So why are there exactly 6 trig functions? And exactly 6. Well, this is climb time, and in this video, we're going to look at the unity of trigonometry. In the first part of this video, we're going to look at patterns within trigonometry and set ourselves up for everything we need to know for the unit circle. In the second part of the video, we're going to look at the unit circle, how to construct it based on patterns, why it's useful, and why it has to be the way it is. All right, so let's start with, we have a triangle right here, and we have a right triangle, and it's A, B, and C. And so we have 3 sides, A, B, and C. We have this angle called theta. All right, so one thing that we can see is that if we have 3 sides, A, B, and C, then if we want to create a ratio between 2 sides, like B over A or B over C, there's only so many ways we can do this. And we call that a permutation. When we are going to choose from 3 options and we want to choose 2 of them, that's called a permutation. So that looks like this, 3 permutation 2. And the way that works mathematically is you have 3 options. Initially, I can choose A, B, or C. And then for my second option, I can choose 2. And so there's a total of 3 times 2, 6 possibilities. So there's 6 possible ways I can choose 2 sides out of those 3. Now, what I'm looking for is ratios. So I'm going to talk about the ratios first, and then I'm going to tell you why they're useful second. So what are my different ratios? One possible ratio is I could take A over C. That's one possible ratio, A over C. Another possible ratio is I could take B over C. That's another possible ratio, B over C. A third ratio I could take is B over A, B over A. All right, and I just told you there's 6 possible ways to create ratios out of these 3 sides. So here's 3 of them. What are the other 3? Well, the other 3 are just going to be the reciprocal of each one of these. So instead of A over C, it's going to be C over A. So I could have that as well. So I could have C over A. And instead of B over C, I could have C over B. Instead of B over A, I could have A over B. So these are the 6 possible ways I can create a ratio of 2 sides when there are 3 possible. Now, the reason why we have a permutation and not a combination is because order matters. When you're dividing, which one's in the numerator and which one's in the denominator makes a difference. There's a difference between 4 divided by 2 and 2 divided by 4. That's why there are 6 possible combinations and not just 3. If we were multiplying instead of dividing, there would be only 3 possibilities because the order wouldn't matter. And it would be 3 choose 2. It'd be a combination problem instead of a permutation problem. But because we're dividing, order does matter. And so there's a difference between A over C and C over A. And so that's why, because of the fixed mathematical possibilities, there are only 6 ways, and there are exactly 6 ways to choose any 2 sides if order matters. And order does matter when we're talking about a ratio. So these are 6 possibilities. A over C has a name, and that name that we give it is called cosine. So cosine of theta is how we describe A over C. And B over C has a name, and the way we give each one of these 6 ratios a name, B over C is going to be called sine. And then B over A has a name, and it's called tangent. And these 3 names go with these 3 ratios, cosine, sine, and tangent, based on these 3 combination of sides. And because order matters, whether we go what's in the numerator and what's in the denominator makes a difference. So if we flip it, instead of A over C, we have C over A. That's something new. That's a new number. And so the reciprocal of cosine is called secant. We have a name for that. And the reciprocal of sine is called cosecant. We have a name for that. And the reciprocal of tangent has a name. We call it cotangent. We have a name for that. So that's why there's exactly 6 trig functions, because there's exactly 6 ways to create a ratio of 2 sides. Now, why do we care about the ratio of 2 sides? Why does that matter? Well, the reason why that matters is because triangles are special. Triangles are special in the way that if I have a triangle, so I have an angle right here, and I try to change that angle, I cannot change that angle without changing the opposite side length, assuming the other 2 side lengths stay the same. I cannot change the angle without changing the opposite side length. So there's a fixed relationship between angles and sides. So because there's a fixed relationship, I can identify what that relationship is. Now, it is possible that I can keep the same theta and change the side length b, for example. I can do that by moving this hypotenuse c in, and maybe it's over here now. And maybe this line is parallel to that line. So if this line is parallel to that line, what would happen is this angle here now would be the same as theta. This and theta would be the same. So I can change theta. I'm sorry, I can keep theta the same while changing a side length. But what's going to happen is even though C gets shorter, and even though B goes from this length to this length, and it gets shorter, and even though A goes from this length to this length, and it gets shorter, even though all three side lengths get shorter, they get shorter together and proportionally. So what you can't change is the ratio of any two sides. So if the angle stays the same, the ratio between these two sides will stay the same. So if I move this hypotenuse in a parallel fashion, I will keep theta the same, but the ratio of the sides will always stay the same. C will get shorter, B will get shorter, A will get shorter. And so the ratio of B over A will stay the same. The ratio of B over C will stay the same. The ratio of A over C will stay the same. So the ratios will always stay the same. So that's what's special about triangles. That's why they're stable shapes. That's why you see them in truss structures, in cranes, in buildings and bridges, because they are stable. Maybe you've seen a bookshelf before that is leaned over. It's an older bookshelf, maybe. And the reason why bookshelves can lean over is because they're not made of triangles. They're made of rectangles initially, but then the rectangles turn into parallelograms. So in the case of quadrilaterals, you can change the angles without changing the side lengths. You cannot do that with triangles. So if you change, like I was pointing out before, if you change the angle, you necessarily have to change the opposite side length. Assuming you keep the other two sides the same. So there is a fixed relationship between angles and sides, and that's what makes triangles special. See, these are the 6 trig functions that are possible when you choose 2 sides out of the 3 possible. Okay, so when we say cosine theta, we're not saying anything magical. All we're saying is we want the ratio of those 2 sides with respect to theta. Assuming theta is over here, A would be the one that we call adjacent, C would be the hypotenuse, and this is right triangle trigonometry. We are assuming that we have a right triangle there. All right, one more thing I want to point out real quick, and that is that the cosine of theta, which is right here, which is A over C, will always equal, if I look at this angle up here, I can create an angle up here, and maybe I'll call it alpha. It'll always equal the sine of alpha. And this is something that's interesting and true about right triangles, that the cosine theta, which is A over C, will always be the sine of alpha, which is also A over C. They have the exact same ratios. In other words, A over C will equal A over C. So this is something that's cool and interesting about triangles. One of the interesting consequences of these ratios of sides is that if I'm looking at this angle, then the cosine of this angle is going to be A over C. And if I'm looking at this angle up here, the sine of that angle up there is also equal to A over C because sine is opposite over hypotenuse. So both of them are equal to A over C. So cosine theta is equal to sine of alpha. And what that also means is that the cosine of one angle will be the same as the sine of the complement of that angle. So for example, if this is 30 degrees, the cosine of 30 degrees will be equal to the sine of 60 degrees. These two angles have to be complements of each other. These two angles have to add up to 90 degrees because in a triangle, all 3 angles add up to 180 degrees. And so if this one's fixed at 90 degrees, that means these two have to add up to 90 degrees as well. So an example of this would be cosine of 30 degrees has to equal the sine of 60 degrees. And the reason for that, as I mentioned, is that these two have to be complements of each other. And we know that the cosine of this one has to equal sine of this one because they're both equal to the same ratio of the same 2 sides. All right, so that is the 6 trig functions. And I want to look specifically now at special triangles. So I want to look at the case of an equilateral triangle. So equilateral triangle. So if we look at an equilateral triangle, that means, by definition, all 3 sides will have the same length. So that means this side is the same as this side, which is the same as this side. So let's look at an equilateral triangle. So if it's an equilateral triangle, that means we know that the sum of 3 angles in every triangle have to add up to 180. That's why these two have to add up to 90. And so therefore, each one of these have to be 60 degrees. So this has to be 60 degrees because it's an equilateral triangle. Now, if I drew a line down the middle, which we often do, because it's convenient, it creates right triangles, which is nice. Now I have this situation I was talking about before with the 60 degrees, and now this is 30 degrees, and this is 90 degrees. And so I have that situation right now. So I have what's called a 30, 60, 90-degree triangle. And this is a special triangle because there's really kind of two special triangles. One is equilateral, one is isosceles. Now look at that isosceles triangle just a little bit. But what's true about this, and let's assume for a second now that the hypotenuse is 1, that's a length of 1, is that I know if this is 1, then I know that this is going to be half of that because it's an equilateral triangle. So this is 1, and so this has to be exactly half of that, which is 1/2. So I know that this is 1/2, and now I know the ratio of two sides. If it's an equilateral triangle, I split it in half. That gives me then the right triangle that I'm looking for. And so now the ratio of two sides would be 1/2 over 1 based on 60 degrees. So I could say the sine of 30 degrees is 1/2 over 1. So you can see that sine of 30 degrees is 1/2 over 1. I'll write that down. Sine of 30 degrees is 1/2 over 1, which is just 1/2. But also the cosine of 60 degrees is 1/2 over 1. So the cosine of 60 degrees gives us the same thing, which is 1/2 over 1. So we know the sine of 30 and the cosine of 60. Now I can use the Pythagorean theorem to find this side here. So let's do that real quick. So the Pythagorean theorem says that a squared plus b squared is equal to c squared. And so that means I have 1/2 squared. And then I have b, which is going to be the one I'm looking for, is equal to 1 squared, which is just 1. So therefore, b squared is going to equal 1 minus 1/4, which is 3/4. And so take the square root of both sides. And so b is equal to the square root of 3 over 2. All right, now that we've found the length of this side, we can find the other sine and cosine. We have the sine of 30, which is this side over that side. And we have the cosine of 60, which is also this side over this side. But since we didn't know this side, we had to use the Pythagorean theorem to find it. Now we know it. So now we can find the cosine of 30 degrees, which is again going to be this side, the adjacent over the hypotenuse. So the cosine of 30 degrees, I'll write it up here. Cosine of 30 degrees is going to equal square root of 3 over 2. That's going to be the adjacent over the hypotenuse. Well, the sine of 60 degrees is also square root of 3 over 2 over 1. I forgot the over 1, but over 1 is still itself because you have to use the hypotenuse. Anything divided by 1 is itself. Now the sine of 60 degrees is going to be the same thing because the sine of 60 degrees is opposite over hypotenuse. So it's also square root of 3 over 2, all over 1, but we don't have to write the over 1. So the cosine of 30 is the same as sine of 60, and the sine of 30 is the same as cosine of 60. And it comes from the equilateral triangle, assuming the equilateral triangle has a length of 1. So if we draw a line down the middle, we'll bisect the opposite side here. If we draw a line down the middle and we make these both right angles, then we necessarily bisect this side. So this is 1/2. And then using Pythagorean theorem, we find out this is square root of 3 over 2. And that's how we identify the ratio of the sides for 30, 60, 90-degree triangles. So that is one special type of triangle that's taken from the equilateral triangle. And that's why we care about the 30, 60, 90-degree triangle. Now let's look at another special kind of triangle, and that would be the isosceles triangle. The isosceles. So you have, whoops, isos. Well, that was a C, not an E. Okay, let's fix that. All right, you get to see how I erase here. That's okay. Isosceles. There we go. The isosceles triangle. All right, so the isosceles triangle means that two sides are the same length instead of three sides the same length. So that's going to look something like this. We have this side here. We have another side here. And this side here is the same length as this side. Now, this is a right triangle. A right triangle that's isosceles in length, which means these two are the same. And we'll assume that the hypotenuse is going to be the longest side, and it will be 1, like before. And now what we know is that these two angles have to be the same. So if everything adds up to 180 and this is 90, that means these two have to add up to 90. And that means this has to be 45 and this has to be 45. So both of these angles are 45 degrees. I don't know if I can write it in and make a big mess here. So 45 degrees there and 45 degrees there. All right, so because they are the same angle, because it's an isosceles triangle, that means sine and cosine are going to give us the same result, because the sine of 45 is going to be this over 1, and the cosine of this 45 up here will be this over 1. But because they're both 45, then it doesn't matter which side you're doing sine, which side you're doing cosine. So the sine and cosine come out to be the same thing. But we do have to figure out what this length is down here. So again, we're going to have to use the Pythagorean theorem for that. So let's see if we can squeeze this in here. So we're going to use a squared plus b squared is equal to c squared. That's the Pythagorean theorem. What we know is that the hypotenuse is 1 here. So we have a squared. Now, because these are the same length, this will also be a squared. So we get a squared plus a squared equals 1 squared, which is just 1. So that means we have 2a squared is equal to 1. And so then we divide by 2 and take the square root. And so a is going to equal 1 divided by the square root of 2. Now, we don't often like to have square roots in the denominator. Makes it hard to compare to fractions a lot of times if there's a square root in the denominator versus the numerator. So what we often do is we rationalize the denominator. So we multiply the numerator and the denominator by the square root of 2. And so if we do that, then a will come out to be square root of 2 over 2. So a is equal to the square root of 2 after 2. And that's what happens after we rationalize the denominator. All right, so that means the side lengths are both square root of 2 over 2. So this is square root of 2 over 2, and this is also square root of 2 over 2. And that happens when the hypotenuse is 1. So that means the sine of 45 degrees, which is also equal to the cosine of 45 degrees, is going to equal square root of 2 over 2 over 1. Square root of 2 over 2 over 1. And we don't have to write the over 1, so square root of 2 over 2. So the cosine of 45 degrees is the same thing as the sine of 45 degrees, which is square root of 2 over 2. So as a reminder, the sine of one angle will be equal to the cosine of its complement. And because the complement of 45 is 45, that means sine of 45 and cosine of 45 give us the same ratio of sides, which is square root of 2 over 2. And you can see it right here by just doing the Pythagorean theorem, assuming these two sides are the same length. Okay, so we have the equilateral triangle, and that gives us the sine and cosine of 30 and 60. We have the isosceles triangle, and that gives us the sine and cosine of 45. And the last thing we want to do is look real quick at what happens if I have an x and a y axis. I changed the brightness there. X and y axes, and what I have is maybe a circle here. I'll just draw a part of the circle. And if I have a spot on the circle right here, let's say the circle has a radius of 1. So we're going to look at the unit circle in just a little bit. Let's assume that circle has a radius of 1. What is true about the x and the y value here? So this spot right here on the circle has got to have an x value and it's going to have a y value. So what is true about that x and that y? Well, we know that we can draw a triangle, and we know that this part here is going to be our x, and it's a right triangle, and this part here is going to be our y. So here's our x and here's our y. So our x is going to be associated with one side length of this right triangle, and our y is associated with another side length of the right triangle. If the radius is 1, that means that the length on the hypotenuse is 1 here. And depending on my angle here, so I don't know the angle, I'll just call it theta for now. Depending on my angle determines what x and y are. So if I take the cosine of theta, it's going to equal my adjacent over my hypotenuse, which is x over 1, which is x. And if I look at the sine of theta is going to equal the opposite over the hypotenuse, which is y over 1, which is y. So x turns out to be just cosine of theta. It is the same thing. If your radius is 1, if you have a circle with radius 1, cosine of theta, x will be the same thing. Sine of theta and y will be the same thing. And in the same way, tangent of theta is going to be, what's theta? Tangent of theta is going to be y over x. It's going to be opposite over adjacent. Okay, tangent theta is y over x. So all three trig functions can be identified from the x and y point of some point on this circle. There's a relationship between the angle that comes up from that point. And there's a relationship between that angle and the x and y values. So cosine is x, sine is y, and tangent is y over x. In the same way, we can find the other three trig functions because they are reciprocals. Secant theta is the reciprocal of cosine. So if cosine is just x, or x over 1, that means secant will just be the reciprocal of that. It'll be 1 over x. In the same way, cosecant will be the reciprocal of y over 1. It'll be 1 over y. And cotangent will be the reciprocal of y over x. It'll be x over y. So we can get all trig 6 functions just out of the coordinate point x and y. Okay, so I think that's going to set us up for the unit circle. Okay, I had to take the glass off and trace a circle because if you've seen in my other videos, I'm horrible at drawing circles. And straight lines are not easy for me either. So I used a ruler for the straight edges, for the straight lines. And then I used the bottom of a coffee cup for the circles. So I got something that looks pretty good as a circle and straight lines. And it's not super precise, but hopefully you can see what we're trying to go for here. These are the angles that are special that we care about, 30, 60, 90, and then add another 30, add another 60, add another 90, and so forth. And these are the 45 degrees, 45, 90, another 45, another 45, another 45, another 45, and so forth. So this is called the unit circle. It's called the unit circle because it is a circle with radius 1. So the unit circle means it is 1 unit in radius. The radius is 1, so that's why we call it the unit circle. And then what we talked about is where this comes from, why the sine and cosine of 45 are both equal to square root 2 over 2. That's the ratio of sides when there is a 45-degree angle in a right triangle. This is the ratio of sides for cosine and sine. When there is a 30-degree angle for cosine and a 60-degree angle for sine, it's square root 3 over 2. And it's the same triangle, but opposite angle. So if you look at the opposite angle, it becomes 1/2. And so we looked at all these things and we're going to now fill out the unit circle. So here's the unit circle. We have an x-axis and a y-axis. And because it's a unit circle, we know that this point right here is going to be 1, 0, because the x value is 1 and the y value is 0. We know this point here is going to be, I'm going to try my best not to smear this, 0, 1. All right, and then we know that this point over here is going to be negative 1, 0. And then this one down here is going to be 0, negative 1. And that's just your x and y value based on the fact that this is a circle of radius 1. So this down here is going to have 0x and negative 1y and so forth. And here's all our x's and y's. All right, and so what we're going to try to do is we're going to try to figure out what points all of these lines are on the unit circle, because those points will be we can get our 6 trig functions from those points, from the x and y value, as we just saw. But first, let's go through and label how many degrees everything is. So let's start with the 90 degrees. So we know that this is 90 degrees. And we know this is 180 degrees. We know this is 270 degrees. And then this is 360 degrees, or 0 or 360 degrees. So add 90, add 90, add 90, add 90. So these are x and y axes. And so if we want to find the cosine of 90 degrees, it's 0. If we want to find the sine of 180 degrees, it's 0. If we want to find the sine of 270 degrees, it's negative 1 because the sine is the y value. Cosine is x, sine is y. If we want to find the tangent of 90 degrees, it's going to be 1 over 0. Can't find it. It's indeterminate because you can't divide by 0. You want to find the tangent of 180 degrees, it's 0 over negative 1, which is 0. So our x and y can give us sine, cosine, tangent, and it can give us the other 3 trig functions as well. We just have to find the reciprocal. That's all we have to do. All right, well, we see the pink one out here. Pink one here is at 60 degrees. So this one out here is 6 degrees in. So 60 degrees up, and then another 60 over here gives us 120 degrees. Another 60 gives us 180. Another 60 gives us 240 down here. And another 60 here gives us 300. And then finally, we have another 60, which is 360 degrees. So those are all angles, 60, 120, 180, 240, 300, that are multiples of 60. Now let's look at our angles that are multiple of 30s. So this is 30 degrees up, so 30 degrees. Add another 30, you get 60. Add another 30, you get 90. Add another 30, you get 120. Add another 30, you get 150 degrees. So this is 150 degrees. Add another 30, you get 180. Add another 30, you get 210 degrees. Add another 30, you get 240. Add another 30, you get 270. Add another 30, you get 300. Add another 30, you get 330. So I want to show you how easy it is to fill out the unit circle if you understand the patterns. You understand the X and Y values on the axes. You understand the angles that we basically have multiples of 30, 30, 60, 90, but I start with the bigger ones first. So I start with the 90, so 90, 180, 270. Then I do 60, 60, 120, 180, 240, 300. Then I do 30, 30, 60, 90, 120, because they're already filled in. So that's kind of nice. Then 150, 180, 210, 240, 270, 300, 330. And so they're 30-degree chunks. And the only thing we're missing so far is the 45-degree chunks. So this is 45 degrees to here. And so we got 45 and then 90. And then 90 plus 45 is 135 degrees. So this is 135 degrees. Plus another 45 gives us 180. Plus another 45 gives us 225 degrees. Plus another 45 gives us 270. Plus another 45 gives us 315 degrees. And plus another 45 gives us 360 degrees. So those are all of our angles in degrees. But when we're working in calculus, we prefer radians. So radians is more common and more popular than degrees is. So let's go ahead and identify now radians. So the way radians works is pi is the same thing as 180 degrees. So this is going to be pi out here. So here's 0, here's pi, and if it came back, this would be 2 pi, but this would be exactly half a pi, so this is pi over 2. And then this down here is going to be, so here's 1/2 pi, here's 2/2 pi's, here's 3/2 pi, which I'm going to write it below here so we can see it. So this is 3/2 pi, and then this is 4/2 pi or 2 pi. So this is 0 or 2 pi right here. So there's our radians for pi. Now I'm going to do it for the 60 degrees, the next biggest one. So this 60 degrees is 1/3 of 180 degrees. So therefore, it's 1/3 of pi. So 60 degrees is pi over 3. So that's 1/3 of pi. Now, if I went to 120 degrees, I now have 2/3 of pi. So 2 pi over 3, 2 pi over 3. And then 3 pi over 3 would be pi. 4 pi over 3 would be right here. So I'm going to put in 4 pi over 3 right here. And then 5 pi over 3 would be right here, 5 pi over 3. And then 6 pi over 3 is 2 pi. So 1/3, 2/3, 3/3, 4/3, 5/3, 6/3, 2 pi. All right, so now let's do the next biggest. Well, actually, let's do the green one next. Let's say kind of like with multiples of 30. So this 30 degrees is 1/6 of 180 degrees. So therefore, it's 1/6 of pi. So this right here is pi over 6. So that's 1/6 pi. This is 2/6 pi, which is the same thing as pi over 3. This is 3/6 pi, which is the same thing as pi over 2. This is 4/6 pi, which is the same thing as 2 pi over 3. This is 5/6 pi, so I'm going to write that in. 5 pi over 6. So 5/6 pi. 6/6 pi. 7/6 pi, so 7 pi over 6. 8/6 pi, which is the same as that. 9/6 pi, which is the same as that. 10/6 pi, which is the same as that. And finally, 11/6 pi. All right, so there's all my radians. Now I have all my radians. So now what I want to do is actually find my coordinate points on the unit circle. So starting with this green one here, 30 degrees. Well, actually, I showed why this is true earlier in the video. So we remember that cosine is like our x, and sine is like our y. So our x, cosine of 30, is square root of 3 over 2. And sine, which is our y, is going to be sine of 30 degrees is going to be, sine of 30 degrees is equal to 1/2. So we've got square root of 3 over 2, 1/2. And what's really cool about this is you only have to remember 3 numbers. Square root of 3 over 2, 1/2, and square root of 2 over 2. because this one up here, and I'll do this one in orange. This one here is, oh, you know what? I never did my orange ones. Now I'm looking at it. Okay, so let's do the orange ones. So the orange ones are 1/4 of pi, because this is pi over 2, so this is half of a half, which is a fourth. So this is pi over 4. Pi over 4. So here's 1/4 pi, 2/4 pi, 3/4 pi. So let's write that in, 3/4 pi. 4/4 pi, which is pi. 5/4 pi. 5/4 pi. 6/4 pi. 7/4 pi. So here's all our proportions of pi based on just going around the circle. 1/4, 2/4, 3/4, 4/4, 5/4, 6/4, 7/4, 8/4, which is 2 pi. All right, so like I was saying is the nice thing about this is you only have to remember 3 numbers, square root of 3 over 2, 1/2, and the other number you have to remember is square root of 2 over 2, which is right here. And that's both the cosine and the sine of 45. So right here, the cosine and the sine of 45 is square root of 2 over 2. And so where am I going to draw this? I think I'm going to draw a little arrow out here. So we've got square root of 2 over 2 and another square root of 2 over 2. All right, and hopefully all that comes in and you can see all that okay. So that is the cosine of 45 degrees, or pi over 4, is square root of 2 over 2. The sine of 45 degrees is also square root of 2 over 2, because that's the y value. So the y is the sine, the x is the cosine. So square root of 2 over 2, square root of 2 over 2. And those are the only 3 numbers you have to remember. Square root of 3 over 2, 1/2, and square root of 2 over 2. Because after that, all you have to recognize is the symmetry and the patterns. So what we know is on this one is 60 degrees. So we know that 60 degrees is the complement of 30 degrees. Since 60 degrees is the complement of 30 degrees, what that means is your sine and cosine just switch. That the cosine of 60 is the same as the sine of 30, which is 1/2. So that means, I'll draw a little arrow here. So we get 1/2 for our cosine, and we get square root of 3 over 2 for our sine. All right, and that's how we can remember it. We can remember it based on just the fact that the 60 is the complement of 30, so therefore sine and cosine are switched. So the only 3 numbers you have to remember is square root of 3 over 2, 1/2, and square root of 2 over 2. And you do have to know some of this information in order to fill out these 3 numbers. But if you know these 2 are the same because it's 45 degrees, then that's helpful. If we know that 60 is the flip of 30, then as long as you know 30, you can put 60 in. Now from here, it's pretty easy to do because it's all based on symmetry. So whatever is true here is also going to be true here. It's just instead of going right, we're going to go left and up. So this one right here is going to be the same x value, but negative. So instead of 1/2 going this way, it's 1/2 going this way. So it's going to be 1/2, and then it's going to be square root of 3 over 2. Okay, so it's 1/2 going left and square root of 3 over 2, but since it was 1/2 going left, it's negative. I don't know if we can see that. I'm going to have to do some erasing here. Try that again. Negative 1/2. It's got negative 1/2 and square root of 3 over 2. So if we go right 1/2 and go up square root of 3 over 2, for this one we go left 1/2, that's why it's negative, and up square root of 3 over 2. And for this one down here, it's similar, except we go left and we go down. So that means it's negative and negative. So I'm going to draw an arrow, running out of space here. So it's going to be negative 1/2 and negative square root of 3 over 2, because it's left and down. So this was left and up, so this is left and down, so it's negative, negative, but it is the same x in magnitude, and it's the same y in magnitude. And then this one here, similar idea. I'll try to draw it in here, except this time we're going positive in the x direction, so it's positive 1/2. We're going down in the y direction, so it's negative square root of 3 over 2, okay? All right, so this one, it's positive and negative. So if you understand the patterns, you can fill out everything in the unit circle just from knowing these 3 pieces of information: the square root of 3 over 2, the 1/2, and the square root of 2 over 2. And as we learned earlier in the video, where the square root of 3 over 2 and 1/2 come from is just a special 30, 60, 90-degree triangle. And looking at that and understanding the Pythagorean theorem and how that works, and then the square root of 2 over 2 comes from the special isosceles triangle and the fact that the 2 sides are the same. That's where we get a square root of 2 over 2. But once you understand these 3 numbers, you can fill out everything else accordingly. And so the unit circle is very useful in that way, because Well, first of all, it has to be what it is because of the patterns and the symmetry, and hopefully you can see the patterns and symmetry. But it's also useful because we can find any trig function of any one of these angles by just looking at the x and y values. So this one here is going to be like this green one over here, except we're going left and up. So we're going to go left, negative square root of 3 over 2, and we're going to go up 1/2. Okay, so this point here is negative square root of 3 over 2 over and 1/2 up. So it's the same as this, except we have to go left instead of go right to get to that spot. All right, and then this one would be similar. I'm not going to fill out everything here. I'm going to fill out this one. This one, we're going to go right, which is square root of 3 over 2. And then instead of going up, we're going to go down. So it's negative 1/2. So we go right square root of 3 over 2, and we go down 1/2. So that's the point there. All right, so this is the unit circle. And the reason why the unit circle is nice is it allows us to find any trig function of any one of these angles, which are kind of our special angles, and any multiple of these angles. So every multiple of pi over 6, some of the multiples of pi over 6 around here. But if you add 2 pi to pi over 6, the reason why it's a single circle is that it comes around to the same thing. Sine and cosine are periodic, which means they repeat. Whatever you get here, you're going to get over here, and you're going to get over here. So if you know what the sine of pi over 6 is, then you can add 2 pi to that, which means you're just going around the circle one more time. And the sine of pi over 6 plus 2 pi is going to be the same value. So every addition of 2 pi to any one of these angles, we also know. So not only do we know all of these angles and all the trig functions for all these angles, but we know every angle plus another 2 pi, and plus another 2 pi after that, plus another 2 pi after that. So we know a lot of angles just by looking at the unit circle. All right, so let's just look at a couple examples so we can see how this works. So let's say we want to find the sine of, choose any one of these random angles. Maybe I'll choose something where I've already filled in the values, like 4 pi over 3. Let's say we want to find the sine of 4 pi over 3. Remember, what sine is, it's a ratio of sides. That's what it is. That means it's a fixed triangle with a fixed angle, and we know that two particular sides will have a fixed ratio. And that fixed ratio of 4 pi over 3 is going to be the y value here, negative square root of 3 over 2. That's the sine of 4 pi over 3. Well, what about, let's do another one. What about the tangent of 11 pi over 6? What about the tangent of 11 pi over 6? So tangent, again, same thing. It is a fixed angle we're talking about, and that fixed angle will produce a fixed ratio between two sides. In this case, the two sides are opposite and adjacent, but that fixed ratio is going to be the y over the x at pi over 6. So the y over the x. So it's negative 1/2 over, so I'll put that in, negative 1/2 over square root of 3 over 2. And the 2's end up canceling out, so you get negative 1 over square root of 3, which we can rationalize that, and you get negative square root of 3 over 3. But that's how you get tangent, just from looking at the unit circle. What about the secant? Let's do the secant of, let's say, pi over 4. Well, secant, again, just like any of the other trig functions, the secant is a fixed angle on a right triangle, and therefore we're looking at the ratio of two sides, and the ratio of two sides, while the side lengths themselves can be different, the ratio of those two sides cannot change. And so the secant of pi over 4 is the reciprocal of the cosine. And so the cosine is the x value, which is square root of 2 over 2. And so therefore the reciprocal of square root of 2 over 2 is 2 over square root of 2, because it is just the reciprocal of that. Just flip it. Instead of square root of 2 over 2, it's 2 over square root of 2. And you can rationalize that. It becomes 2 times the square root of 2 over 2, or square root of 2. All right, so that's the secant of pi over 4. So we can find all 6 trig functions for any one of these angles, and any one of these angles plus 2 pi. And that's why the unit circle is nice, but it's easy to fill out if you understand the patterns. All you really have to remember, which I showed you why these things were true early in the video, but all you really have to remember is square root of 3 over 2, 1/2, and square root of 2 over 2. Everything else comes out of the mix as a result of understanding the patterns and how things fit together.